in general, American options are much harder to price than European options, but not if you have a binomial tree model. Okay? For one stock only. Okay, binomial trees get complicated if you have many correlated stocks, many trees. But if you have only one stock, American option in a binomial tree is almost as easy to price as a European option. So let's see how to do that. I'll first give you kind of a general formula for American options, Martingale pricing formula, risk-neutral pricing formula, without any proofs, just maybe a little bit of intuition, and then we'll apply it in a binomial tree. Okay, so I'm going to consider an American option that pays G of tau, this is just a notation, G of tau dollars if exercised at time tau, before maturity. Okay, so that's just notation, how much the option pays if it's exercised at time tau. And tau can be random. Okay? Typically, for a call option, you would exercise when the underlying stock hits, let's say, I don't know, $300. So the optimal exercise strategy is exercise the first time the stock hits $300. That's a random time. You don't know when that's going to happen. Right? So in that case, tau is the first time of hitting 300, but it's a random time. It may never happen actually before maturity, in which case you just don't exercise. All right, so here's the formula, and in fact, forget about this max first, and let's fix tau. So we know that this is the risk-neutral pricing formula if maturity was in fact tau. Even if it's random, it would be still the same formula, even if tau is random, if maturity is random. So discounted, payoff, take expectation at time t, that's the price at time t for a European version under Martingale probability. Okay? From the point of view of, take a point of view of the seller of the option. Okay? The seller of the option doesn't know when the holder, the buyer, will exercise the option. So if he wants to be conservative and be sure that he will be able to pay off this option, he has to take the worst case scenario. And the worst case scenario is to charge the highest possible price, which would be the maximum over all maturities of European option prices. Okay? So from the point of view of the seller, he should be happy, intuitively speaking, with charging the maximum of European options, or maximum overall possible maturities between small t and capital T, including random maturities. Okay? That's where the difficulty comes in general. You have to take a maximum over these random maturities, not just deterministic maturities. These are called optimal stopping problems in stochastic control, stochastic optimization theory. And these are not easy problems, sometimes easier, sometimes harder, but in general not easy. Okay? So it's kind of mathematically, you have an optimization problem, and computing an expected value is like a linear problem, if you want, and optimizing over expected values makes the problem nonlinear. Okay? But that's just mathematical language. The point is, it's typically harder, not in the binomial tree, as we will see, but that's kind of the intuition from the point of view of the seller. Now, it turns out that in a market which is complete and there is only one queue, also the buyer will be happy with this price. It's not necessarily easy to prove, but it can be proved that the buyer will also be able to replicate the payoffs he will get in the future. And if he starts with this price, buys for this price, and both will have, there is 100% replication on both sides, they will both have zero profit losses in a complete market. Intuitively, why is the buyer also happy? Because the buyer can, in fact, choose tau to attain this maximum. It's up to the buyer to decide which tau, so he or she can choose tau which attains the maximum, and then she will be able to hedge 100%. All right. So there is something called a dynamic programming principle, DPP, or dynamic programming principle for these type of problems, stochastic optimal control, optimal stopping problems. In this version, if it can be written like this. Again, like for European option in binomial tree, I want to make a connection between today and t plus delta t, today plus delta t. Okay? Here I have the connection with possible maturities, but here I want a connection from t to t plus delta t. So the dynamic programming principle, which I will not prove, but it's also intuitive, hopefully, says that the price today of an American option is a maximum between two things. One thing, and let me look at this thing first because this is familiar. This is like the European price, right? So this is like if I decide to wait, and then it would be like a European option, and this would be the value, just expectation of e to the minus half delta t g or t plus delta t. So the value of waiting one more period is here. So I compare that, the value of waiting, to the value of immediate exercise. Because g of t is by definition what I get if I exercise now and don't wait. Okay? So I'm comparing again, comparing the value of waiting, sorry, that's the value of waiting, the European type price, to the value of exercising right now. Okay? So intuitive enough. I can only make, it's a simple control problem at each step. I only can make a decision to wait or not to wait, okay, or exercise. It's a binary decision. That's why it becomes easy here. Either I wait or I don't, and I compare those two values. If I don't wait, I get this. If I wait, this is the fair value of waiting. One more period. In the binomial model, I can write this as before, as a q times upper value of my option at t plus delta t plus 1 minus q down value. I mean upper value meaning if stock went up and if the stock went down. And discount, okay, compare that to g of t. And that's the value of my American option. So it's going to work the same in a binomial tree. I'm just going to go backwards, but instead of just computing these expected values, I'm also going to be comparing with the value of immediate exercise, and I will take the maximum at each node. And then I'll continue averaging backwards, taking maximum, averaging, discounting, taking maximum. That's it. Yeah? So just one more step of just this comparison. This I have to compute anyway, even for the European option, and then I'll just compare it to, and this is going to be easy to compute, just how much I will get if I exercise at a certain node in the binomial tree. Fine. It's pretty much as easy as as computing European option prices. So let's do an example, the same example. Okay, before the example, this is the graphical representation again, same as before. I know these values at the end and maturity. I average, discount, and then I do maximum of what I could get right now, which I'm denoting A. And the value here is just g of s u squared. And here it would be g of s times u times d. Here g of s d times d squared. Okay, so each time I do a maximum of whatever would be this a is going to be different in different nodes. And then again, I go backwards, discount, average, do maximum, so on. That's just a visual representation. Similar example, except I'm going to take a put option because we know that with call options, if there are no dividends, the price is the same as for American and the European price are the same, so that would not be very interesting. There would never be exercise. So let's do a put option. Same data as before. $100 starting stock price, today's stock price, 1.1 for U, 0.9 for D, strike price 100, 0.05. We computed P star or Q, 0.7564, delta T is 1. Same stock prices, that didn't change. I'm just changing the option, 100, 110, 121, 99, 90, and 81. Now I start computing the option price. and this is the put option. So at the end, if we get to the end, the price of the stock is 121. 100 minus 121, it's a put option. Strike price 100 minus 121, that's negative. Take the maximum, it's 0. 100 minus 99, that's $1. If I'm holding a put option, I'm going to be making a $1 profit here. 100 minus 81, $19. Okay? So these are my put option values if I wait to maturity, depending on where the stock ends up. Fine. Now I have to compute these values here, which I claim as something like 0.23 and 10. So I'm doing that in the next slide. And this is the same as before, Q. All right, so this bottom value, how do I get that? So I do this average of 1 and 19. Remember in the previous slide, we had 1 in the upper, lower. So just look at the picture. Right? So we had 1 here, 19 here. So this is, I have to Q times 1, 1 minus Q times 19. So that's what I'm doing. I'm doing Q times 1 plus 1 minus Q times 19. Discount. That's 5.1229. But I'm taking maximum of that in 10. Why 10? I have to go back to the picture again. Here, the value of the option, if I exercise, is 100 minus 90, which is 10. Yeah. Put option, 100 minus 90. 10 is the... So I do a maximum of 10, and that number, which was smaller than 10, so the maximum is 10. Okay? So here, in fact, if I come here, if I believe this model, and my stock price goes down to 90, I would exercise if I hold the option. It would be optimal because the value of exercise 10 is higher than the value of waiting, which was that average value and discounted of 5 something. Yeah? So here I would exercise, and the value would be 10. I would just get 10. Let's compute this one. So what is the value here if you exercise, by the way? Actually, it's 0, right? It's 100 minus 110. It's negative. Maximum is 0. So here we will just have to do the same thing as in the European case. It has to be that one because exercising would give you 0. Okay, so the upper numbers were 0 and 1. Just remind ourselves of that. And with 0 here, 1 here. So Q times 0 plus 1 minus Q times 1. That's what we are doing now. Q times 0 plus 1 minus Q times 1. Discount, maximum is 0, something, 0.2318. Fine. So that gives me the value at that node in the tree. So I have prices at time 1, 0.23 or 10. And now I repeat the procedure. Q times 0.2318, 1 minus Q times 10, discount. And then I have to take a maximum. What is the value here if I exercise? It's again 0. It's 100 minus 100. I wouldn't exercise right away. It would be 100 minus 100. I would get 0. So I just have to do the European thing also here because the maximum is with 0. Okay, so let's look at the numbers. Q times 0.2318, 1 minus Q times 10. Discount, maximum is 0. It's going to be this number. If you compute it, it's 2.4844. So if this model is good enough for you, you would charge, as the seller of the option, you would charge something like $2.5 for one option of this kind. And as a buyer, you would also be happy if you believe in this model again. You would be happy with this price. All right. So we have learned how to compute prices in binomial trees for path-independent options. Okay? It may be somewhat more complicated doing it for path-dependent options. I'm not going to discuss that now. But in principle, we know how to price basic vanilla options in the binomial tree. What we don't quite know is how to choose. Okay, the interest rate has to be estimated. Delta t, I told you, you choose basically one day, but we don't know how to choose u and d. Okay, but that I will talk about later. Maybe quickly, just if you are impatient and cannot wait. So typically you take u equal to 1 over d. So I just have to choose one of these. And typically you do something like u is equal to e to the sigma. For those of you who know already the notation of Black-Scholes, sigma is the volatility of the stock. So basically like the variance of log returns of the stock. We'll talk about this later again, but for those of you who already are familiar, basically you choose u as volatility of the stock, e to the volatility of the stock times square root of delta t. And volatility of stock is something which people know, or at least there are many methods of estimating it and deciding what the volatility value is. So there are ways people deal with how to choose the volatility. So I will talk about this later, but just for those of you who like to make a connection if you already know something about Black-Scholes. All right, that's it for now.